In this video, we're going to make a note of why two crucial input functions called impulse or step functions are used so frequently in control theory. To illustrate that importance, if you take a look at the Python help manual for the signals that we've been using for Laplace transform and state space, you'll see that we used this form before to simulate our output. And that was kind of the generic control tool for pretty much anything. We could set our control to be some function of time and it would do the simulation for us. Literally the only two other things that do simulations that are provided with this kit, which tells you how relevant and important they are in day-to-day practice, are ones based on what's called an impulse and what's based on a step function. So the step response of a continuous time system or the impulse response are two phrases that you're going to hear quite frequently. You're going to see them in any control theory analysis. So what are those and why are they so central? Like, why are they the only other thing that does simulations in this toolkit? Well, let's see. First off, let's talk about the impulse response. So an impulse is equal to the delta function. And again, graphically, that's our spike up here that has area 1, but time interval effectively 0. It's a limiting process, but still. So an impulse is this. And if we do an impulse at time 0, that is simply delta of t. When we transform that, we get e to the negative 0 times s, which is of course just 1. Now you can imagine this is a convenient thing to have in your transform function because it just ends up not affecting anything mathematically. All right, so that's the impulse. The step is what we call here the Heaviside function. And it looks like, sorry, it's called h of t. And the step function is 0, 0, 0, 0, and then it jumps up to a 1 value and then goes on forever after that. So that's against time, that's our h of t. So this is like flipping a switch. And if you can imagine, a lathe or some kind of spinning motor, sometimes you flip the switch and things kind of take a while to get going. The step is what you're applying by flipping a switch. You're saying, okay, I'm providing a constant energy supply to this system. And then the response is this motor starting to speed up and accelerate and reach some kind of speed. In the long run, that would be the response to a step function. So how does that play out in the math here? Well, again, we'd have h of t, but it would just be with no shift in it. So h of t, when we transform it, is going to equal e to the negative 0, and it's going to just be 1 over s. E to the 0 over s gives us 1 over s. So this is the impulse, that's the step. How does that play a role in how we analyze these systems? So if we do the impulse, that lets our u of s equal the Laplace transform of a delta function, which we just said was equal to 1. So our x of s is equal to 1 over s plus k times b, which is equal to, or tells us that we're going to get our behavior, x of t is equal to a constant times the natural behavior of the system. So when you see what the impulse response to a system is, it is essentially the natural behavior of the system, maybe scaled up by something or down by something. The metaphor used is, I hit the system with a hammer, what does it do? The idea is you've hit it and then you're not doing anything else. So all you see is what the system would naturally do going forward in time. And that's actually true for both of these. So if we had the impulse over here, we would have x of s, so impulse again, we would have x of s equals 1 over ms squared plus cs plus k times b times 1. And so again, when we do the inverse transform, x of t would simply be some scaling factor times the natural behavior. Here, natural oscillations, or decays if it happened to be overdamped. Again, it's like you have this mass sitting there, and then you hit it with a hammer and it starts shaking and oscillating. Well, the frequency at which it oscillates and the speed or how quickly it damps down is all coming from the natural behavior of your particular mass, damping coefficient, and spring constant. Now, the downside of the impulse is, first of all, it's hard to actually do. The mathematical construct, again, of this perfectly spiked value, which has exactly area 1, a little hard to engineer. The second issue is that it's hard on systems if you slam them with functions like that. So an alternative that produces very similar results is to use the step function instead. Now, a step function still has a little bit of nastiness. When we turn it on, there's a rapid change, but at least it stays on for a while. And so if we do the step function, what we get is our u of s is equal to the Laplace of the Heaviside function, just that on-off function, or off then on function, and it's 1 over s. And so our x of s then is equal to the transfer function times b times 1 over s. Now, this is less obvious than I would like ideally, but what I'm going to do is harken back to first year calculus, where you learned about a technique called partial fractions. And we're not going to make you do this by hand. What I am going to ask you to do is think about what it means. Partial fractions was where you had, let's put this in the right form here, so it looks like it, s plus k times s with a common denominator. When you have this kind of form, partial fractions will let you decompose this. Let me move it over to here. It'll let you decompose this into something over the s plus k plus something else over the s. Well, how does this help you? Well, this is the transform of the system behavior. And so in the time domain, your x of t is going to be equal to a sum of a times the e to the minus kt's plus b times, well, the transform of 1 over s, we just go back for a few steps here, 1 over s is the same as a constant. Now you might think for a second, wait a minute, wasn't 1 over s the transform of h of t? It turns out it doesn't matter because we never care about what happens to the left of time 0. So whether you call it something that was off and then on, or whether it's just on, it's the same as long as you're only ever looking at positive time values, which fortunately is what we're doing here. So you can think of it as just a constant when we're going in this direction. It's just easier to reason about it that way. And again, this is the natural behavior of our system. The transfer function is what we would get here. We just have a slightly different scaling factor on it, but it's essentially the s plus k that we had in our transfer function, which is the natural behavior. We see that plus a shift. And it would be a vertical shift if we're talking about graphs here. So what we're going to see out of this is if we put a step function on for something like the heating cooling system like this, you're going to get a shift up to some value. And here we had it called capital B. And this is our x of t against t. So we're going to have a shift and an exponential decay. And wait, this is exactly what we saw when we were controlling this in some of the Python code. It started at 0 because we were assuming 0, 0 for the start point. And then we're going to see the natural cooling behavior, only now approaching some shifted version instead of approaching the 0 line, which would be our usual default if there was no control being applied. So what's important here? When you apply a step function, you do see the natural behavior and a shift, and the shift is really obvious. It's some constant away from 0. That means everything else that you see is the natural behavior. So when you go and think about the code here, what do people learn when they apply the step function to a system? Well, they get a response back, and that response captures perfectly the natural behavior of the system. Let's take a look at the similar example here with the mass and spring. So the mass spring. What we're going to get there is if we do the step function, and we're going to get the transform again of it of the Heaviside function, our on-off function, is going to be 1 over s. So our x of s is equal to 1 over all these mass and damping and spring coefficients, transfer functions, times b times u of s, so 1 of s, 1 over s, and that gives us, again, if we want, b, ms squared plus cs plus k times s. We would again be able to apply partial fractions. So it's no longer a product, but it is now some constant over this part. There should be an as plus b here. Quadratics in the bottom get linear terms on top. And then plus c over s. And again, the issue isn't so much what these constants are, it's that this x of t will equal something to do with the natural behavior of the spring system, plus the transform of 1 over s, which is going to be a shift, a vertical shift. And what we're going to get with those graphs is we're going to see a new value here, it'd be c, so we're going to do oscillations around c, and we're going to capture that natural behavior in terms of the frequency, in terms of the rapidity of the decay of the oscillations, all of that natural system behavior captured here, we get to see when we just flip a switch, apply a step function to this, and this graph here is what we would call the step response. It's what the system does in response to a step function input. So what is the lesson from this? The reason these kinds of toolkits frequently only have a generic simulator and then the impulse and step responses is because these are what gets you to the heart of the system itself. If you want to know how your system's going to behave, ideally you can hit it with an impulse, and then what you're going to see back is just the natural behavior of the system. If it turns out impulses aren't actually easy to apply, if instead a step function might be easier to apply, well, you're still going to see some combination of the natural system behavior in terms of how quickly things decay or how fast they oscillate, what kind of frequency they oscillate at, plus some shift. Then you just look at the graph and go, okay, ignore the shift. Let me figure out how quick this decay is happening for this system. This really helps to understand the dynamics of the system. You can look at this graph and go, oh, I see how long it's going to take to achieve certain goals. Maybe I like that, maybe I don't. Maybe I choose a different control strategy. You can do things once you've understood the essentials of the transfer function and what it means for the natural behavior. Knowing what the system does in its natural behavior then allows you to answer design questions. What kind of U will help to achieve some other goal that I have for the system?